Every solar panel you see promises cheap energy, but organic versions often fail within months under sunlight. The reason lies in a single chemical failure point that has stalled this technology for years. Researchers have now found a hidden defense mechanism inside DNA itself, turning biological repair into a potential manufacturing blueprint for self-healing materials. This discovery reframes how we might finally build durable, flexible solar cells without the heavy costs of traditional shielding. The core problem with organic photovoltaics is not just that they are less efficient than silicon, it is that their molecular structure collapses under ultraviolet radiation. When sunlight hits these polymer layers, high-energy UV photons break chemical bonds in a process called photo-oxidation. This creates free radicals that chew through the active layer from the inside out. Engineers have tried to stop this with thick coatings of traditional inorganic filters like zinc oxide or titanium dioxide. However, adding bulk blocks light and disrupts the delicate nanoscale morphology required for the cell to generate electricity. The solution has always been a trade-off between protection and performance. Recent research on titanium dioxide nanoparticles interacting with DNA offers a tangible mechanism that changes this equation entirely. Contrary to the typical toxic generation of reactive oxygen species, studies indicate that these specific nanoparticles can stabilize DNA duplexes in a range from 25 degrees Celsius up to 44 degrees Celsius. This interaction induces a binding effect where the structure partially unwinds just enough to absorb UV energy rather than degrading it. The biological observation suggests that embedding DNA nanoparticle composites could extend the operational lifespan of organic solar cells by turning degradation into a reversible state. This breakthrough reframes the failure mode from a permanent material breakdown to a self-healing chemical reaction. In nature, DNA possesses an intrinsic ability to repair UV-induced thymine dimers through enzymatic or photochemical pathways without needing external stabilizers that typically degrade the active layer of a solar cell. By mimicking this process in a synthetic context, we eliminate the need for heavy additives. Unlike traditional inorganic UV filters that add bulk and reduce light absorption, the DNA-based shield operates at the molecular scale. This preserves the critical nanoscale morphology of the bulk heterojunction active layer, which is the primary bottleneck in scaling organic solar cells to commercial viability. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The integration of titanium dioxide nanoparticles with DNA creates a synergistic effect where the inorganic component acts as a sacrificial UV absorber that protects the DNA backbone. Once shielded, the DNA can subsequently repair the organic polymer matrix, effectively turning a biological repair mechanism into a scalable, low-cost manufacturing additive. This means we are not just adding a barrier, we are introducing an active agent that continuously heals damage caused by sunlight exposure. The result is a material system where the very component designed to absorb light also initiates its own recovery process when hit with damaging radiation. However, significant production trade-offs and adoption barriers remain unaddressed before this can become reality in your home or on a factory floor. The current evidence is limited to thermal stability in buffer solutions within a laboratory setting. We lack benchmark data on scalability for industrial roll-to-roll manufacturing processes that produce solar panels at speed. There are no long-term durability tests under full-spectrum outdoor conditions simulating years of rain, heat cycles, and intense UV exposure. Furthermore, the complex interaction between biopolymers and inorganic nanoparticles introduces unknowns regarding manufacturing consistency. Achieving uniform distribution of these particles across a large sheet without clumping is an engineering challenge that has not yet been solved at scale. Cost-effectiveness compared to established inorganic UV absorbers also remains unproven. While the chemistry is promising, the gap between stabilized thermal stability in a lab buffer and a robust, self-healing solar coating requires substantial engineering validation before it can be considered a viable solution for the industry. We must determine if the cost of extracting or synthesizing DNA-compatible nanoparticles outweighs the savings from not needing heavy protective layers. The supply chain implications are significant as we move from chemical synthesis in a flask to continuous manufacturing lines that demand absolute precision and purity. The stakes here involve redefining what is possible for flexible electronics, building integrated photovoltaics, and portable power sources. If this chemistry can be stabilized and scaled, it removes the single biggest failure point in organic photovoltaics, degradation under solar irradiation. This would allow us to build lightweight, bendable panels that last as long as their silicon counterparts without the weight or rigidity. The potential impact on manufacturing is profound because it relies on chemical self-repair rather than external mechanical protection. We are standing at a point where biological insights can solve engineering problems that have persisted for decades. The transition from observing DNA repair in cells to embedding this behavior into solid-state devices requires bridging biology and materials science with rigorous industrial standards. Until we validate the durability under real-world conditions, this remains a promising hypothesis rather than an immediate product feature. The path forward involves proving that the molecular dance observed in buffers can withstand the harsh reality of outdoor operation for decades. The future of organic solar may not depend on finding new polymers or better encapsulants alone. It might rely on borrowing strategies from life itself to create materials that are resilient by design. This approach shifts the focus from preventing damage entirely to enabling rapid recovery after minor incidents, a fundamental change in how we engineer for longevity. The engineering challenge now is translating this molecular miracle into a reliable industrial process that works at scale and delivers cost-effective energy solutions. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.